Something is wrong with the planets. We have been observing them for centuries, mapping their orbits, measuring their masses, cataloguing their properties, but the more we discover, the less sense they make. Planets that should not exist. Orbits that violate every prediction. Atmospheres that defy explanation. Weather patterns that seem impossible. In our own solar system, Neptune radiates more heat than it receives from the Sun. Venus spins backward for reasons no one can explain. Jupiter's core might not be solid at all. And these are the planets we know best. The ones we have visited with spacecraft, the ones we have studied for generations. Beyond our solar system, the mysteries multiply. Hot Jupiters that orbit their stars in hours. Super-Earths that have no equivalent in our neighborhood. Planets made of diamond, planets covered in lava, planets where it rains glass sideways at supersonic speeds. Worlds so strange that discovering them forced us to rewrite the rules of planetary formation. This is not science fiction. These planets exist. We have detected them, measured them, and confirmed their impossible properties. And each discovery raises more questions than it answers. Why do some planets migrate inward while others stay put? How do super-Earths form? What determines whether a world becomes rocky or gaseous? We thought we understood planet formation. We were wrong. The universe contains roughly 100 billion galaxies. Each galaxy contains hundreds of billions of stars. Most stars have planets. The numbers become incomprehensible. Trillions of worlds, maybe more. And we have studied fewer than 10,000 of them in any detail. The ones we have found are the easiest to detect, the largest, the closest to their stars, the most extreme. We are sampling the universe's planetary diversity from the shallow end of the pool. What lies in the deep water terrifies and excites astronomers in equal measure. If the easy-to-find planets are this strange, what about the ones we cannot yet detect? The rogue planets wandering between stars, the worlds in binary systems, the planets around dying stars or newborn stars or stars are nothing like our Sun. Each represents a test case for our theories. And so far, our theories keep failing. This script explores the most mysterious planets known to science, not the most distant, not the most recently discovered, the ones that fundamentally confuse us, the ones that should not exist according to our models, the ones that make astronomers question whether we understand planetary physics at all. These worlds are not just strange, they are impossible, yet they exist anyway. We will journey from our solar system's enigmas to the bizarre exoplanets orbiting distant stars. We will examine worlds where physics seems to break its own rules. And we will confront the uncomfortable truth that the universe's planetary systems are far more diverse, far more strange, far more unsettling than anyone predicted. The most mysterious planets in the universe are not mysteries because we lack data. They are mysteries because the data makes no sense. If you think you understand how planets work, prepare to have that certainty shattered. The cosmos has built worlds our theories cannot explain, and those worlds are waiting to be explored. The planet that defies gravity. Neptune sits at the edge of our solar system, a blue ice giant orbiting 2.8 billion miles from the Sun. It completes one orbit every 165 Earth years. It has 14 known moons and a faint ring system. On paper, Neptune should be unremarkable, just another cold gas giant slowly circling a distant star. But Neptune is doing something impossible. It is generating more heat than it receives. This fact alone rewrites what we thought we knew about planetary physics. The Sun is the solar system's only significant energy source. Planets absorb sunlight, warm up, and radiate that heat back into space. Energy in equals energy out. This is thermodynamics, basic physics. But Neptune violates this balance. It radiates 2.6 times more energy than it absorbs from the Sun. Where is the extra heat coming from? The obvious answer is internal heat. Planets, form hot. Gravitational collapse during formation generates enormous thermal energy. Large planets take billions of years to cool. Jupiter and Saturn both radiate more heat than they receive because they are still cooling from formation. This makes sense. Neptune should work the same way, except it does not. Neptune and Uranus are roughly the same size. They formed at roughly the same time from roughly the same materials. They should have similar internal structures and similar cooling rates, yet Uranus barely radiates any excess heat. Its thermal output matches solar input almost perfectly. Neptune pumps out more than twice the energy it receives. Why? One planet cooling normally, another of nearly identical size flooding space with excess energy. The difference cannot be explained by formation models. Something else is happening inside Neptune, something we do not understand. Some scientists propose that Neptune has an internal heat source, not leftover heat from formation, something actively generating energy deep in the planet. But what? Nuclear fusion requires temperatures and pressures found only in stars. Chemical reactions cannot sustain this output for billions of years. Radioactive decay might contribute, but calculations show it cannot account for the observed energy. Another proposal involves phase transitions. Neptune's interior is mostly water, methane, and ammonia under extreme pressure. These materials might exist in exotic states, superionic water, metallic hydrogen, states that only exist under conditions we cannot replicate in laboratories. If these materials undergo phase transitions, converting from one exotic state to another, they could release energy. But this requires understanding chemistry at pressures exceeding millions of atmospheres. We are guessing. The mystery deepens when we examine Neptune's magnetic field. Most planets with significant magnetic fields have them generated by conducting fluids in their interiors. Earth's magnetic field comes from molten iron in its core. Jupiter's field comes from metallic hydrogen. Neptune's field should work similarly, but it does not. Neptune's magnetic field is tilted 47 degrees from its rotation axis. For comparison, Earth's field is tilted only 11 degrees. The field is also offset from the planet's center. It does not align with any obvious internal structure. The field is strong but chaotic, irregular. It switches polarity in unexpected ways. Computer models cannot reproduce this behavior using standard planetary interior structures. Voyager 2 measured Neptune's field during its 1989 flyby. The data has puzzled scientists ever since. The field suggests Neptune's conducting layer is not deep in the core. It is higher up in the mantle. This implies the interior structure is completely different from what models predict. Maybe there is no solid core at all. Maybe the planet is layered in ways we have not imagined. This connects back to the heat problem. If Neptune's interior is structured unusually, heat transport could be unusual too. Convection patterns might trap heat in certain layers while releasing it from others. This could create the observed energy imbalance. But modeling this requires knowing the interior structure, which we do not. Neptune's atmosphere provides more mysteries. Wind speeds reach 1,200 miles per hour. The fastest winds in the solar system blow on Neptune. This makes no sense. Wind is driven by energy. The Sun provides 900 times less energy to Neptune than to Earth. Neptune should have gentle breezes. Instead, it has supersonic hurricanes. The excess internal heat might power the winds. But energy alone is not enough. You need circulation patterns. Mechanisms to transfer heat from interior to atmosphere. Neptune's atmosphere is mostly hydrogen and helium, with traces of methane. The methane freezes at upper atmosphere temperatures, creating clouds. But the cloud patterns are bizarre. They form and dissipate on timescales of hours to weeks, much faster than Jupiter's clouds, much faster than atmospheric models predict. In 1989, Voyager 2 observed the Great Dark Spot, a storm system larger than Earth, similar to Jupiter's Great Red Spot. But when Hubble observed Neptune in 1994, the Great Dark Spot was gone, vanished, replaced by different storms in different locations. Jupiter's Great Red Spot has persisted for at least 400 years. Neptune's storms come and go like weather patterns on Earth. Why? No one knows. The atmosphere contains methane, about 2% by volume. This gives Neptune its blue colour. Methane absorbs red light and reflects blue. But Neptune appears deeper blue than Uranus, despite Uranus having similar methane content. Something else is contributing to the colour. Unknown atmospheric components, or unknown chemistry, or unknown physics. Recent observations found that Neptune's brightness varies over decades. The planet gets brighter, then dimmer, in cycles lasting 20 to 30 years. This correlates with the solar activity cycle. But Neptune is so far from the Sun that solar variations should have negligible effect. Yet the correlation is real. Neptune somehow responds to solar activity across 2.8 billion miles of space. The planet's rotation adds another wrinkle. Neptune's day is 16 hours long. But determining this was difficult. Unlike solid bodies, gas giants do not rotate uniformly. Different latitudes rotate at different speeds. Different depths rotate at different rates. We define a planet's rotation period by measuring its magnetic field rotation. Except Neptune's magnetic field is so tilted and offset that determining rotation is complicated. Early estimates put Neptune's day at 18 hours. Later measurements revised it to 16 hours. Different measurement techniques give slightly different results. We do not even know for certain how fast Neptune spins. And if we do not know the rotation rate, we cannot model interior structure accurately. Everything connects to everything else. Each mystery reinforces the others. Neptune has 14 moons. The largest, Triton, is itself bizarre. Triton orbits backward. It is the only large moon in the solar system with a retrograde orbit. This means Triton did not form with Neptune. It was captured. Probably a Kuiper belt object that wandered too close and got grabbed by Neptune's gravity. Tidal forces are slowly pulling Triton toward Neptune. In a few billion years, it will cross the Roche limit and be torn apart, creating a massive ring system. But Triton's current orbit creates tidal heating in both bodies. Triton is geologically active. It has geysers spouting nitrogen gas 5 miles high. Neptune, too, might be experiencing tidal heating. This could contribute to the excess heat output, but calculations show tidal heating cannot fully explain the energy imbalance. The mystery of Neptune's heat is not just an academic puzzle, it has implications for understanding all ice giants. Uranus and Neptune are common planet types. We have discovered hundreds of similar worlds orbiting other stars. If we do not understand how Neptune works, we do not understand those exoplanets either. And ice giants might be the most common planetary type in the universe, more common than gas giants like Jupiter, more common than rocky planets like Earth. This matters because planet formation theories depend on understanding heat flow. Planets migrate inward or outward depending on how they exchange energy with their protoplanetary disks. If our energy models are wrong, our migration models are wrong. If migration models are wrong, our understanding of where planets form is wrong. The entire edifice of planetary science rests on thermodynamics. And Neptune does not obey the rules. Some researchers propose that Neptune experienced a late heavy bombardment, a period when many large objects crashed into the planet. These impacts would deliver energy, heat the interior, stir up the internal structure. This might explain both the heat output and the strange magnetic field. But the timing does not work. Such bombardment would have happened early in the solar system's history. billions of years ago. The heat would have dissipated by now. Others suggest Neptune swallowed a large moon, or planetesimal, relatively recently, geologically speaking. Within the last few 100 million years, this would have injected enormous energy into the interior, enough to still be radiating away. But there is no evidence for such an event. No debris field, no unusual chemical signatures, just the heat itself. The truth is, we do not know. Neptune is a mystery. It produces too much heat, it has strange winds, its magnetic field makes no sense, its atmosphere behaves unpredictably, its rotation rate is uncertain, and everything we learn raises more questions. This is not a failure of observation. Voyager 2 gathered excellent data. Ground-based telescopes observe Neptune regularly. The problem is that the data does not fit the theories. Neptune represents a fundamental gap in our understanding of planetary physics. We thought we knew how planets work. We were wrong. And if we are wrong about Neptune, a planet in our own solar system that we have studied extensively, how wrong are we about the thousands of exoplanets we have barely glimpsed? The universe is teaching us humility, one impossible planet at a time. The world that spins backward. Venus rotates backward. This single fact has puzzled astronomers for decades. Every other planet in the solar system spins in the same direction. The direction the solar system itself rotates, counterclockwise when viewed from above the Sun's north pole. This makes sense. Planets form from a rotating disk of gas and dust. The disk's rotation becomes the planet's rotation. Conservation of angular momentum. Basic physics. Venus does not care about basic physics. It spins clockwise, opposite to every other planet, and it spins slowly. One Venus day lasts 243 Earth days, longer than a Venus year, which is 225 Earth days. Venus is the only planet where a day is longer than a year. The sun rises in the west and sets in the east, and it takes 117 Earth days to move from sunrise to sunset. Why? The most common theory is collision. Something massive may have struck Venus early in its history, reversing its spin. This idea explains Uranus's extreme tilt, but Venus is nearly upright, its axis is only slightly inclined. To reverse rotation yet remain upright would require an improbable sequence of impacts. It is possible, but unlikely. Another theory blames tidal and atmospheric torques. Venus's thick atmosphere, which is about 90 times denser than Earth's, responds strongly to the sun's heat. As the upper layers warm and move, they exert drag on the planet below. Over billions of years, this slow friction could have halted Venus's original spin and restarted it in reverse. Models show it is possible, although the details remain uncertain. Whatever the cause, the consequences are dramatic. The slow rotation means no strong magnetic field. On Earth, our magnetic field comes from a rapidly spinning molten iron core. Venus's sluggish rotation cannot sustain a dynamo. Without magnetic protection, the solar wind strikes the upper atmosphere directly, stripping particles away and slowly eroding it. That same atmosphere, however, makes Venus one of the most hostile places in the solar system. Carbon dioxide dominates, trapping heat in a runaway greenhouse effect. Temperatures reach about 900 degrees Fahrenheit, hot enough to melt lead. The pressure at the surface is like being 3,000 feet underwater. Clouds of sulfuric acid shroud the planet, reflecting sunlight and hiding the surface from view. Radar mapping revealed that the surface is surprisingly young, about 500 million years old. Few craters suggest that something catastrophic resurfaced the planet in the recent geological past. Scientists think Venus releases heat in violent, planet-wide volcanic outbursts. Instead of slow tectonic drift like Earth, Venus's crust may melt and reform in massive cycles. The rotation may even influence this process. Because Venus spins so slowly, convection patterns in its mantle differ from Earth's. Heat may build up longer and then release all at once, covering the planet with fresh lava. Its backward spin could be part of this unstable thermal rhythm, with rotation, volcanism, and atmosphere locked in a feedback loop that is still not fully understood. Venus's weather is equally extreme. Winds in the upper atmosphere race around the planet every 4 Earth days, moving far faster than the planet itself spins. This superrotation remains a mystery. On Earth, air is dragged along by the ground beneath it, but on Venus, the atmosphere seems to move independently, driven by solar heating and pressure waves through dense air. From orbit, Venus looks calm, bright, and featureless, but below the clouds, the surface glows orange with heat. Sound travels differently, and objects fall slowly. Soviet probes that landed there survived barely 2 hours before being crushed and melted. They revealed flat plains of rock and a dim amber sky. Venus and Earth are often called twins since they are similar in size, composition, and distance from the Sun. Yet one became a paradise for life, while the other became a furnace. The key difference may be water. Early Venus may have had oceans, but being closer to the Sun, its water evaporated. Water vapor is a powerful greenhouse gas. The more it accumulated, the hotter the planet became. Eventually, ultraviolet light split the vapor into hydrogen and oxygen. The hydrogen escaped into space, and Venus's oceans were lost forever. Without water, there was no plate tectonics, no efficient cooling, and no climate stability. Heat trapped by carbon dioxide baked the surface, creating the inferno we see today. What began as a small difference in distance from the Sun became a planetary-scale divergence between habitability and hell. Venus rotates backward, slowly and stubbornly, against every rule of planetary formation. Understanding why may reveal not just its past, but also our own future. Venus is what happens when a planet much like Earth takes a different path, when feedback loops spiral out of control, and a once livable world becomes a warning written in acid and fire. The giant with no core. Jupiter is massive. It contains more mass than all other planets combined, 318 times Earth's mass. If you gathered every planet, moon, asteroid, and comet that is not Jupiter, Jupiter would still be heavier. It dominates the solar system gravitationally. Its influence extends throughout, yet for all its bulk, Jupiter might be hollow. Not hollow like an empty shell, but lacking a solid core. Most planetary models assume gas giants form around solid cores. Rock and ice accumulate first. Gravity attracts gas. The core grows. Eventually, it becomes massive enough to capture huge amounts of hydrogen and helium from the protoplanetary disk. The gas becomes the planet's bulk, but the core remains at the center. Solid, dense. Jupiter should work this way. Core about 10 to 20 Earth masses. Surrounded by metallic hydrogen. Metallic hydrogen surrounded by molecular hydrogen. Molecular hydrogen transitioning to the atmosphere. Neat layers. Each denser than the one above. This is standard planetary structure. It fits the data. Mostly. Except the Juno spacecraft measured Jupiter's gravity field with unprecedented precision. Gravity measurements reveal internal structure. Variations in gravity reflect density variations inside the planet. If Jupiter has a solid core, gravity measurements would show it. The core would be denser than surrounding material. This would create a gravitational signature. Juno found something unexpected. Jupiter's gravity field is more complex than models predicted. There is no clear signature of a solid core. Instead, the data suggests a fuzzy core, a diluted core, or no core at all. The central region has somewhat higher density than outer regions, but not the sharp boundary expected from a solid core. Scientists propose several explanations. Maybe the core dissolved. Jupiter's interior is hot, millions of degrees. At these temperatures and pressures, rock and ice might dissolve into the surrounding metallic hydrogen, like sugar dissolving in water. Over billions of years, the core eroded, dispersed, leaving behind only a diffuse region of slightly higher density. But dissolution requires specific conditions. The temperature is high enough, pressure appropriate, and time. Calculations suggest dissolution is possible, but slow. Jupiter is 4.5 billion years old. Has it been long enough? We do not know. We cannot test core dissolution in laboratories. The required pressures and temperatures are beyond our capabilities. Another explanation involves giant impacts. Early in the solar system's history, planets experienced violent collisions, giant impact events. If a large object struck Jupiter with enough energy, it could have disrupted the core, broken it apart, scattered core material throughout the interior. This would create the fuzzy core signature Juno observes. Computer simulations show this is possible. A planetary embryo several Earth masses striking Jupiter at high velocity delivers enormous energy. The impact creates shock waves. These propagate through the interior. The core structure breaks down. Core material mixes with surrounding layers. The planet remains intact externally, but internally, structure is disrupted. However, the timing matters. Such an impact must have happened early, before Jupiter fully formed, while it was still accreting gas. If the impact happened later, after Jupiter reached full size, the planet would have reaccumulated a core. We see no evidence of recent impacts large enough to destroy Jupiter's core. So if impact is the answer, it happened billions of years ago. And we have no direct evidence of such ancient events. A third possibility is that Jupiter never had a solid core. Core accretion theory assumes cores form first, then capture gas. This is standard. But some models suggest gas giants can form differently. Through gravitational instability, a region of the protoplanetary disk becomes gravitationally unstable. It collapses directly into a gas giant, no core required. Gas, dust, and ice collapse together. The resulting planet is made of mixed materials throughout, no distinct core layer. This explains Juno's observations. No sharp core boundary because there never was a core. Jupiter formed through direct collapse. But gravitational instability requires specific disk conditions. High mass, rapid cooling. It works in the outer solar system, where disks are massive and cold. Jupiter formed closer to the Sun. Conditions might not have been right for gravitational instability. Most models favor core accretion for Jupiter. But we cannot rule out instability. The mystery extends beyond the core. Jupiter's magnetic field is the strongest in the solar system, generated by metallic hydrogen in the interior. Metallic hydrogen is hydrogen under such extreme pressure that it behaves like a metal, conducts electricity, flows like fluid. This conducting fluid generates Jupiter's magnetic field through the dynamo effect. We have never produced metallic hydrogen in laboratories. It requires pressures exceeding 1 million atmospheres. Some experiments claim to have created it briefly. Others are skeptical. We know metallic hydrogen exists inside Jupiter because the magnetic field requires it, but we do not know its properties. How does it behave? How does it flow? What is its viscosity? These questions affect how the dynamo works. Jupiter's magnetic field has unusual features. It is tilted 10 degrees from Jupiter's rotation axis. It is also lopsided. The field is stronger in the northern hemisphere than the southern, and there is a great blue spot, a region where the magnetic field is anomalously weak. These features suggest the interior structure is complex, not uniform layers as models assume. The fuzzy core might explain this. If core material is dispersed unevenly, density variations occur. These affect convection patterns. Convection drives the magnetic field. Uneven convection creates an uneven magnetic field. The great blue spot might mark a region where convection is weakest, or where core material is concentrated. Juno is measuring both gravity and magnetic field, trying to connect them, build a complete picture of the interior. But Jupiter does not cooperate. The data is complicated. Different models fit different aspects of the data. No single model fits everything. We thought Jupiter would be relatively simple. A ball of gas with a solid core, neat and understandable. Instead, Jupiter is messy, complex, defying easy categorization. This has implications for understanding gas giants everywhere. We have found thousands of Jupiter-like planets around other stars. Hot Jupiters, warm Jupiters, cold Jupiters. We classify them by mass and temperature. We assume they have cores like we thought Jupiter had, but if Jupiter does not have a clear core, maybe those exoplanets do not either. Our entire framework for understanding gas giant interiors might be wrong. Jupiter also creates problems for planet formation theory. Core accretion is the standard model. Cores form first, then capture gas. This explains rocky planets. It explains ice giants. And it was thought to explain gas giants. But if Jupiter has no core, or a dissolved core, or a disrupted core, core accretion has problems. Maybe gas giants form differently than smaller planets. Maybe the formation process erases cores. Maybe our understanding is incomplete. Some researchers propose hybrid models. Jupiter started with a core, formed through core accretion, but then something happened. Impact, dissolution, migration. The core changed, lost its sharp boundary, became fuzzy. This preserves core accretion while explaining observations, but it adds complexity, requires additional processes. Each process brings new uncertainties. The alternative is accepting that gas giants form in multiple ways, some through core accretion, others through gravitational instability. Each path produces planets with different internal structures. Jupiter might be an unstable planet. Saturn is a core accretion planet, or vice versa, diversity rather than uniformity. This fits observations, but it makes prediction harder. If formation processes vary, we cannot assume exoplanets follow rules derived from solar system giants. Jupiter's atmosphere provides more mysteries. The visible atmosphere is turbulent. Bands, spots, vortices. The Great Red Spot is a hurricane larger than Earth that has persisted for at least 400 years. We do not know why it lasts so long. Earth's hurricanes dissipate in days to weeks. Jupiter's storms endure for centuries. The atmosphere is mostly hydrogen and helium, with traces of methane, ammonia, water, and other compounds. These trace chemicals create colours, the red, brown, and white bands. But the exact chemistry is unknown. We have theories: ammonia ice, ammonium hydrosulfide, complex organic molecules. But confirming composition requires direct sampling. And Jupiter's atmosphere is hostile. Pressure increases rapidly with depth. The temperature rises. Spacecraft cannot survive deep penetration. In 2003, the Galileo spacecraft plunged into Jupiter's atmosphere, sent data until it was crushed and melted, but it only penetrated about 150 kilometers, a tiny fraction of Jupiter's depth. Below that, we rely on models, and models depend on assuming internal structure. If the structure is not what we assume, models are wrong. Jupiter emits more heat than it receives from the Sun, like Neptune, but Jupiter's excess heat is easier to explain. Jupiter is still contracting slowly, losing gravitational potential energy. This energy becomes heat. Jupiter is still warm from formation, cooling gradually over billions of years. This process explains the heat output. Unlike Neptune's mysterious excess, Jupiter's makes sense, or so we thought. Recent measurements suggest Jupiter's cooling rate has changed. It cooled faster in the past. Now it is cooling slower. This implies something inside Jupiter has changed. Perhaps phase transitions in the interior. Hydrogen changes from molecular to metallic form at specific pressure and temperature. If those conditions shifted, the cooling rate would change. But what causes conditions to shift? We do not know. Jupiter has at least 79 moons. Some are large. Galilean moons, Io, Europa, Ganymede, Callisto. Each is a world unto itself. Io is the most volcanically active body in the solar system. Europa has a subsurface ocean. Ganymede is the largest moon in the solar system and has its own magnetic field. Callisto is ancient and heavily cratered. These moons formed from the disk of material around young Jupiter, or they were captured. The evidence is mixed. The moons interact with Jupiter gravitationally. Tidal forces heat their interiors. This heating powers Io's volcanism, keeps Europa's ocean liquid. The moons also exchange angular momentum. This affects orbits, slowly changes their configurations. Understanding Jupiter requires understanding its moons. The system is interconnected. Jupiter's rings are faint. Discovered by Voyager 1-inch 1979. Made mostly of dust. The dust comes from impacts on Jupiter's small inner moons. Micrometeoroids strike the moons. Eject dust. Dust spirals inward toward Jupiter. Some enter the atmosphere. Some stay in orbit, forming rings. The rings are temporary on cosmic timescales, constantly replenished by impacts. If impacts stopped, the rings would fade in centuries. Jupiter protects Earth. Its gravity deflects comets and asteroids. Many objects that would otherwise strike Earth hit Jupiter instead, or are flung out of the solar system. This gravitational shepherding might have been essential for life's development on Earth. Without Jupiter, Earth might have experienced far more impacts. Too many for complex life to develop. Jupiter as guardian, protector of the inner solar system. But Jupiter also disturbs. Its gravity prevents planet formation in the asteroid belt. The belt contains enough material to form a planet, but Jupiter's perturbations stir things up. Velocities increase. Collisions destroy rather than build. No planet forms, just rubble. Jupiter gives with one hand and takes with the other. Understanding Jupiter is fundamental to understanding the solar system, and understanding solar systems in general. Gas giants shape their systems. They migrate, disturb orbits, capture or eject smaller bodies. The configuration of our solar system reflects Jupiter's influence, and the configuration affects habitability, affects where life might arise. Yet Jupiter itself is not understood. Its interior is uncertain. Its core is ambiguous. Its magnetic field complex. Its atmosphere is dynamic. It is the most studied gas giant. We have sent multiple spacecraft, made countless observations, and still Jupiter surprises us. The giant with no core. The planet made of crystal. 55 Cancri E orbits a sun-like star 40 light-years from Earth. It completes one orbit every 18 hours. The planet is twice Earth's size and 8 times its mass. Surface temperature reaches 4,400 degrees Fahrenheit, hot enough to melt iron, hot enough to vaporize rock, and according to the best models, the planet might be made of diamond. Not entirely diamond, but a substantial fraction, perhaps a third of its mass, a world wrapped in crystalline carbon, glittering if anyone could see it, except the heat makes it glow red hot, like coal in a furnace. This is not speculation. The composition follows from observations and physics. 55 Cancri E is a super-Earth, larger than Earth but smaller than Neptune. we have no equivalent in our solar system. Super-Earths are common around other stars, but studying them is difficult. They are too small to see directly. We detect them through their gravitational effects on their host stars, or by the slight dimming when they pass in front of the star. Transit observations reveal the planet's size. Radial velocity measurements reveal its mass. From size and mass, we calculate density. 55 Cancri E has a density about 7.2 grams per cubic centimetre. For comparison, Earth's density is 5.5. Iron has a density of 7.9. The planet is denser than rock, but not quite as dense as pure iron. This density constrains composition. The planet cannot be mostly hydrogen and helium. Too dense. Cannot be mostly water or ice. Still too dense. It must contain significant amounts of heavy elements. Carbon, iron, silicon, oxygen. The question is proportions. The host star provides a clue. 55 Cancri has an unusual composition. It is rich in carbon relative to oxygen. The carbon to oxygen ratio is about 1.12. For comparison, the Sun's ratio is 0.54. This matters because planets form from the same material as their stars. A carbon-rich star likely has carbon-rich planets. On Earth, oxygen is more abundant than carbon. Oxygen combines with silicon to form silicates. Rocks, minerals. The crust and mantle are silicates. Carbon exists but is less common. It forms carbonate minerals, coal, diamonds under rare conditions. Earth is an oxygen-rich planet orbiting an oxygen-rich star, but 55 Cancri E formed in a carbon-rich environment. When carbon exceeds oxygen, chemistry changes fundamentally. Instead of silicates, carbon forms carbides. Silicon carbide. Carbon itself. Under high pressure, carbon becomes graphite or diamond. The planet's interior might contain vast quantities of crystalline carbon. Diamond layers stretching hundreds of miles deep. The idea sounds like science fiction. A planet made of diamond, worth unimaginable amounts if we could mine it. But economics breaks down on cosmic scales. The planet is 40 light-years away. No technology exists to reach it, and even if we could, the heat and pressure would destroy any mining equipment. The diamond planet is untouchable, but fascinating. The planet's extreme temperature comes from proximity to its star. It orbits closer than Mercury orbits our Sun, 10 times closer. At this distance, stellar radiation is intense. The planet absorbs enormous energy. Surface temperature stays above 3,900 degrees Fahrenheit. The night side is slightly cooler, about 2,000 degrees, but not much cooler. Heat redistributes through the atmosphere. Weight? Atmosphere? Yes. 55 Cancri E has an atmosphere despite the extreme heat. Observations by the Hubble Space Telescope detected hydrogen and helium. The atmosphere is not thick, but it exists. This was surprising. At such high temperatures, lighter elements should escape, hydrogen especially. Its low mass means high thermal velocities. Fast-moving molecules exceed escape velocity. The atmosphere should have been stripped away billions of years ago, yet it persists. This suggests the atmosphere is constantly replenished, possibly by volcanic outgassing. The intense tidal forces from being so close to the star generate internal heating. This powers geological activity, volcanism, lava flows. These release gases trapped in the interior. The gases form an atmosphere. Solar radiation strips it away. Volcanism replenishes it. A dynamic equilibrium. The planet is tidally locked. One side always faces the star. The other side faces space. This should create extreme temperature differences. The day side blazing hot. The night side is freezing cold. But observations show the night side is much hotter than expected. Heat is transported from day side to night side, either through atmospheric circulation or through the planet itself. If through the atmosphere, we need fast winds. Supersonic winds capable of carrying enormous heat. Computer models can produce such winds, but they require specific atmospheric properties, and we do not know the atmosphere's composition beyond hydrogen and helium. Heavier molecules might be present. Carbon monoxide, carbon dioxide. Metals vaporize from the surface, each affects heat transport differently. If through the planet, we need high thermal conductivity. Diamond has the highest thermal conductivity of any natural material at room temperature. If 55 Cancri E contains substantial diamond, heat could conduct through solid carbon layers. Dayside heat flows through the planet to the night side. This would equalize temperatures somewhat. Observations do not distinguish between atmospheric and internal heat transport. Both might occur. The diamond hypothesis has other evidence. Seismic models show that diamond stability depends on pressure and temperature. At Earth's surface, diamond is metastable. It wants to convert to graphite, but the conversion is slow. Diamonds persist for millions of years. At higher pressures, diamond is fully stable. Below about 100 miles depth in Earth's mantle, conditions favor diamond over graphite. On 55 Cancri E, with 8 times Earth's mass, internal pressures are much higher. The entire mantle could be in the diamond stability field. And if the composition is carbon-rich, diamonds would form naturally. Not just small crystals, massive diamond structures, layers kilometers thick. Perhaps the entire mantle crystallized as diamond during planetary cooling. This would affect the planet's evolution. Diamonds are very hard. It resists deformation. Plate tectonics might not operate. Earth's mantle is solid but ductile. It flows slowly over millions of years. This flow drives plate tectonics. But diamonds are too rigid. A diamond mantle would lock the crust in place. No tectonic recycling. Heat escapes only through volcanism and conduction. The planet's magnetic field depends on internal dynamics. Earth generates its field through a liquid iron core that circulates. This requires sufficient heat flow from core to mantle. On 55 Cancri E, the diamond mantle might insulate the core. Prevent heat escape, the core stays hot, but circulation might be sluggish or absent. If the core does not circulate, no magnetic field generates. We have not detected a magnetic field around 55 Cancri E, but detection is difficult at that distance. The planet is too small and too far for current instruments to measure magnetic fields directly. We can only infer. If the planet has no magnetic field, stellar wind strikes the atmosphere directly. This enhances atmospheric erosion, requires even more vigorous volcanic replenishment to maintain the hydrogen-helium atmosphere. The diamond planet challenges formation theories. Standard planet formation occurs in protoplanetary disks. Dust grains collide, stick together, grow into planetesimals. Planetesimals collide, form protoplanets. Protoplanets continue growing. Eventually, they will become planets. This process depends on material composition. In oxygen-rich environments, silicate dust dominates. Grains stick efficiently. Planet formation proceeds normally. In carbon-rich environments, carbon dust prevails. But carbon grains behave differently. They stick less efficiently. Planet formation might be slower or work differently. We do not fully understand planet formation in carbon-rich systems. 55 Cancri E is one of 5 known planets in the 55 Cancri system. The others are gas giants, more typical. Super-Earth is unusual. It might have formed farther out, where temperatures were cooler, then migrated inward. Migration is common for planets. Interactions with the protoplanetary disk cause orbits to change. Planets spiral inward or outward. If 55 Cancri E formed farther out, it would have formed in cooler conditions, less extreme. It might have started as an icy planet, but migration brought it close to the star. Intense heat evaporated any water or ice, drove off lighter elements. Only the dense core remained. Carbon-rich because the system is carbon-rich. The extreme heat maintained carbon in crystalline form. This migration scenario fits observations, but it is not proven. Alternative scenarios exist. Maybe the planet formed in place, close to the star. In the disk's hottest regions, dust grains sublimated. Only the most refractory materials remained. Carbon, iron, these condensed to form planets. A planet born in fire, rather than migrating into it. Observations of 55 Cancri continue. The Spitzer Space Telescope measured its thermal emission. Hubble studied its atmosphere. James Webb Space Telescope recently observed it. Each observation adds details, refines models. The planet's mass is well known. Its radius is well measured. Its temperature was confirmed, but composition remains uncertain. Some scientists question the diamond hypothesis. They point out that even in carbon-rich environments, some oxygen exists. Oxygen and carbon combine to form carbon monoxide. This removes carbon, reduces the amount available to form diamonds. Maybe the planet contains less diamond than initial models suggested. Maybe it is mostly silicon carbide with some diamonds, or mostly graphite with diamond only in the deepest layers. The debate continues, but regardless of exact composition, 55 Cancri E is bizarre. A super-Earth orbiting every 18 hours, surface glowing red-hot, possibly wrapped in layers of crystalline carbon, with a thin atmosphere constantly replenished by volcanism, tidally locked but somehow transporting heat from dayside to nightside. Every detail raises questions, and 55 Cancri E is not unique. We have found other super-Earths around carbon-rich stars. They might also contain substantial diamonds. Some orbit even closer to their stars, even hotter, even more extreme. The universe produces planets we never imagined, worlds that challenge our assumptions. That forces us to expand our definitions of what a planet can be. The diamond planet represents the diversity of exoplanets. Each planetary system is unique, formed from different materials, under different conditions. Our solar system is just one example. An oxygen-rich system with a specific set of planets, but the universe contains countless other examples. Carbon-rich systems, iron-rich systems, water-rich systems. Each produces different planets. Understanding this diversity is the frontier of planetary science. We can no longer rely on solar system examples alone. We must study exoplanets, even though they are distant, even though observations are difficult, because exoplanets teach us what is possible, what nature creates given different ingredients and different conditions. 55 Cancri E is a laboratory, an extreme experiment in planetary formation and evolution. Its existence proves that super-Earths can form in carbon-rich environments. Those planets can survive extreme heat, that atmosphere can persist in hostile conditions, that diamond can exist on planetary scales. Each fact is a data point. Each data point constrains theories. The planet is too far to visit, too hot to land on. We will never walk on its diamond surface, never mine its crystalline depths. It will remain a distant world observed only by telescopes. But it will never stop being fascinating, never stop challenging our understanding, because 55 Cancri does something no solar system planet does. It shows us what happens when carbon rules instead of oxygen. When extremes become normal, when the impossible becomes real, a planet made of crystal, glowing in the darkness, orbiting a distant star, forever beyond reach but never beyond imagination. This is the universe we live in, where planets are not just rocks and gas, they are diamonds and mysteries. The world that rains glass. HD 189733b looks beautiful from a distance. Deep blue, cobalt, reminiscent of Earth when seen from space, but the resemblance ends there. This is not a water world. The blue comes from silicate particles in the atmosphere, and those particles form clouds made of molten glass. That rains sideways at 5,400 miles per hour. The planet is a hot Jupiter, 2.9 million miles from its star, completes one orbit every 2.2 days. Tidally locked, one side eternally faces the star, the other faces perpetual night. Dayside temperature reaches 2,000 degrees Fahrenheit, hot enough to vaporize most metals, hot enough that silicates remain gaseous. But the night side is cooler, around 1,200 degrees Fahrenheit, still incredibly hot by Earth standards, but cool enough for silicate vapor to condense, form particles. These particles are tiny droplets of molten silicate and glass. They form clouds on the night side, then strong winds transport them toward the day side. As they move into hotter regions, they vaporize again. The cycle repeats endlessly. The winds are among the fastest in the known universe. Driven by extreme temperature differences between day side and night side, hot air rises on the day side, flows toward the night side at high altitude, cool, sinks, returns to the day side at low altitude. This circulation creates jet streams. Winds reach thousands of miles per hour, supersonic, hypersonic even, fast enough to strip flesh from bone. If there were any flesh or bone to strip, the glass rain particles move with these winds, accelerated to tremendous velocities. When they encounter anything, the impact is devastating. A particle the size of a grain of sand traveling at 5,400 miles per hour hits with the energy of a bullet. Millions of particles, each a microscopic projectile. The atmosphere is a sandblasting furnace. This is not speculation. We have observed HD 189733b extensively. The Hubble Space Telescope measured its color. Multiple ground-based telescopes monitored brightness changes. Spitzer Space Telescope mapped temperature distribution. Observations agree. The planet is deep blue. Temperature varies by 800 degrees between dayside and nightside. Winds are extraordinary. But why is it blue? Glass itself is not blue. Pure silicon dioxide is transparent or white. The blue color requires something else. Aluminum oxide possibly, or other metal oxides mixed with the silicate. These give the molten glass a blue tint, like cobalt blue glass on Earth. But determining exact composition is difficult. We observe the planet's spectrum, but the spectrum is complex. Many absorption and emission features, overlapping, difficult to disentangle. One confirmed component is sodium. The planet's atmosphere contains sodium atoms. We know because sodium has distinctive absorption lines in the yellow part of the spectrum. These lines appear strongly in HD 189733b's spectrum. Sodium vapor at high temperatures, glowing, absorbing starlight, creating the signature we detect. Carbon monoxide is also present, detected through infrared spectroscopy. Carbon monoxide forms at high temperatures from carbon and oxygen. It is stable in the hot atmosphere. Water vapor might be present too. Some spectral features match water, but conformation is uncertain. Water at such high temperatures behaves differently than water on Earth. It dissociates, breaks into hydrogen and oxygen, reforms. The equilibrium is complex. The planet's mass is 1.13 Jupiter masses. Its radius is 1.14 Jupiter radii. This means its density is similar to Jupiter's. Mostly hydrogen and helium, a gas giant, but with trace chemicals that create its distinctive color and weather. The trace chemicals matter because they absorb heat, affect temperature structure, influence atmospheric dynamics. HD 189733b's orbit is extremely close to its star. This proximity means intense tidal forces. The star's gravity pulls harder on the side of the planet facing the star than on the far side. This creates tidal bulges. The planet stretches. Stress builds in the interior. This stress generates heat through friction, tidal heating, similar to how Io is heated by Jupiter, but more intense because HD 189733b is so much closer to its star. Tidal heating might contribute to the planet's hot night side. Heat generated in the interior flows outward, reaches the surface, radiates into space. This internal heat source supplements the starlight, helps explain why the night side is not colder. But calculating tidal heating requires knowing the planet's interior structure, which we do not know precisely. The planet was discovered in 2005 using the transit method. When the planet passes in front of its star, the star's brightness dims slightly. By measuring the amount of dimming and the duration, astronomers calculate the planet's size and orbital period. HD 189733b was one of the first exoplanets where atmospheric composition was measured. It became a benchmark for studying hot Jupiter atmospheres. Hot Jupiters were a surprise. When the first exoplanets were discovered in the 1990s, many were gas giants, orbiting very close to their stars. This was unexpected. In our solar system, gas giants are far from the Sun. Jupiter is 5 astronomical units away. Saturn even farther. Gas giants should form beyond the frost line, where water ice is stable. Close to the star, temperatures are too high for ice. Without ice, not enough solid material exists to form large cores. Without large cores, gas giants should not form. The solution is migration. Gas giants form farther out, then move inward. Interactions with the protoplanetary disk cause angular momentum transfer. The planet loses energy. Its orbit shrinks. It spirals toward the star. Eventually, something stops the migration. Maybe the disk dissipates. Maybe the planet reaches the star's magnetospheric cavity. Migration halts. The planet remains in a close orbit. HD 189733b migrated. It formed farther out where ice could condense, built a massive core, captured gas, became a gas giant, then migrated inward over hundreds of thousands or millions of years. Ended up in its current orbit. The migration erased evidence of its formation. We see only the end point, the hot Jupiter, blue and deadly. The extreme conditions create unusual chemistry. Atmospheric chemistry on Earth depends on temperature, pressure, and available elements. Oxygen and nitrogen dominate. Water forms clouds. Weather is driven by water phase changes. Evaporation, condensation, precipitation. This is familiar chemistry, comfortable chemistry. HD 189733b has alien chemistry. Temperatures high enough to keep metals gaseous. Magnesium, iron, sodium. These elements float in the atmosphere, react with oxygen, form oxides. The oxides condense into particles when they reach cooler regions. These particles are the glass rain, but not pure glass. Metal-contaminated glass, blue glass, raining sideways in hypersonic winds. Some models suggest the atmosphere contains clouds at different altitudes. Each cloud layer is made of different materials. High-altitude clouds of silicates, mid-altitude clouds of metal oxides, low-altitude clouds of sulfides or chlorides. Each layer has different colors, different optical properties. The planet's appearance depends on which layers are visible from outside. The deep blue color, visible from space, might be a high-altitude haze. Particles suspended above the main cloud deck. These particles scatter light, preferentially scatter blue light because they are small, similar to why Earth's sky is blue. Rayleigh scattering, but in HD 189733b, the scattering particles are molten glass instead of air molecules. The mechanism is similar. The materials are wildly different. Observations show the planet's brightness varies. It gets brighter and dimmer over time. These variations are too rapid to be explained by orbital changes. They must be atmospheric. Weather patterns, cloud formations, perhaps massive storms similar to Jupiter's Great Red Spot, but evolving much faster, forming and dissipating in days or weeks. The planet's magnetic field is uncertain. Gas giants typically have strong magnetic fields. Jupiter's field is the strongest in the solar system, generated by metallic hydrogen in the interior. HD 189733b probably contains metallic hydrogen too. Its mass and composition are similar to Jupiter's, but whether it generates a magnetic field depends on rotation rate and internal convection patterns. We do not know these precisely. If the planet has a magnetic field, it might interact with the stellar wind. The star emits charged particles. These particles flow outward, encounter the planet's magnetosphere. The interaction creates aurora, like Earth's northern and southern lights, but far more intense. Energies millions of times greater. The entire planet might glow with auroral light. Add this to the thermal glow from high temperatures. HD 189733b is a light show, a spectacle, devastating and beautiful simultaneously. The planet's proximity to its star creates another effect: X-ray and ultraviolet radiation. The star emits high-energy photons. These strike the upper atmosphere, ionize atoms, break molecules, create a hot ionosphere. The ionosphere is plasma, electrically conducting. If the planet has a magnetic field, the ionosphere and field interact. Energy flows between them, creates currents, heats the upper atmosphere further. This heating causes atmospheric escape. Light elements evaporate into space, hydrogen especially. The planet is slowly losing mass, not quickly, a few tons per second. Sounds like a lot, but the planet is enormous, in 1027 kilograms. Losing a few tons per second, it would take trillions of years to evaporate completely. Still, the process is happening. The planet is shrinking, extremely slowly, but measurably. Some of the escaping material forms a tail, a comet-like trail of hydrogen atoms streaming away from the planet. This tail is detectable. Observations during transit show extra absorption in hydrogen lines. The star's light passes through the tail. Hydrogen absorbs some light. We see the absorption. Measure the tail's extent. HD 189733b's tail extends several planetary radii behind it, a ghostly wake marking its passage through space. The glass rain is confirmed by multiple lines of evidence. Spectroscopy shows silicate features. Temperature maps show cooling in regions where condensation should occur. Brightness variations match predictions for cloud formation. Computer models reproduce the observed properties when they include silicate clouds and extreme winds. The conclusion is robust. HD 189733b has weather unlike anything in our solar system. But details remain uncertain. Exactly how much silicate exists? How large are the particles? Are they liquid droplets or solid shards? How do they form? How do they fall? Do they reach the lower atmosphere or vaporize at high altitude? Each question requires more detailed observations, or better models, or both. James Webb Space Telescope observed HD 189733b, measured its thermal emission across multiple wavelengths, mapped temperature structure in detail, found evidence for temperature inversions. In Earth's atmosphere, temperature decreases with altitude. In HD 189733b's atmosphere, temperature increases in some layers. This creates thermal inversions, stable layers that suppress vertical mixing. These inversions affect cloud formation and wind patterns. But understanding their cause requires knowing what molecules exist in those layers. JWST is working on it. The planet represents extremes: extreme heat, extreme winds, extreme chemistry. It pushes physical limits, tests our understanding of atmospheric physics, weather modeling, chemistry under extreme conditions. Every observation challenges assumptions, forces refinement of theories. HD 189733b is a laboratory, but one we cannot visit, cannot touch, can only observe from 63 light-years away. That distance is both a blessing and curse. Blessing because the planet would kill any spacecraft instantly. Curse because observations are difficult. The planet is small, faint. Most of its light is reflected or emitted starlight. Separating the planet's signal from the star's signal requires precise measurements, advanced telescopes, careful data analysis. Even then, we see only averaged properties, the entire planet's spectrum blended together. We cannot resolve features, cannot watch individual storms, cannot measure local conditions. Yet we learn. Each observation adds information, constrains possibilities, rules out models, supports others. The picture grows clearer. HD 189733b is less mysterious than when first discovered, but new mysteries emerge. Every answer raises new questions. Why is the blue color so strong? How do winds accelerate to such high speeds? What stops atmospheric escape from being faster? How stable are these conditions over time? The planet has existed for billions of years. Its star is similar in age to the Sun. The planet formed early in the stellar system's history. It has been a hot Jupiter for most of its existence. Billions of years of glass rain. Billions of years of hypersonic winds. Billions of years of brutal conditions. The planet endures, unchanged, unyielding. This endurance fascinates. On Earth, conditions change over time. Climate shifts, oceans rise and fall, continents drift, life evolves. Everything is dynamic. But HD 189733b seems static. The same temperature, the same winds, the same glass rain, forever, or for as long as the star shines. When the star dies billions of years from now, the planet will die too, engulfed or ejected, but until then, the glass rains, sideways, endlessly. A world that rains glass, blue and terrible, beautiful and deadly. Proof that the universe creates planets beyond imagination, beyond comfort. Places where physics operates at extremes we cannot replicate, cannot survive, can only observe and wonder. HD 189733b is not a mystery because we lack data. It is a mystery because the data reveals something so alien we struggle to comprehend it. A planet where weather is a weapon, where clouds are shrapnel, where survival is impossible and beauty is measured in shades of blue. The planet that shouldn't exist. WASP-12b is dying, slowly torn apart by its star. Yet it should have died long ago. should have been consumed millions of years in the past. But it persists. Orbiting closer than any planet its size should be able to survive. Every day, it loses mass. Every orbit brings it nearer destruction. Yet somehow, impossibly, it continues to exist. The planet orbits its star every 26 hours. One day, the orbital distance is less than 2 million miles. For comparison, Mercury orbits the Sun at 36 million miles. WASP-12b is 18 times closer to its star than Mercury is to ours. This proximity subjects the planet to extreme tidal forces. The star's gravity tries to tear it apart, and succeeds partially. The planet is bloated. Its radius is twice Jupiter's radius, but its mass is only 1.4 times Jupiter's mass. This means extremely low density, about 0.15 grams per cubic centimeter. For comparison, Earth's atmosphere at sea level has a density of 0.001 grams per cubic centimeter. WASP-12b is denser than air, but not by much. It is more like a gas cloud than a solid object. The planet is puffed up, inflated to an absurd size. Why so inflated? Tidal heating. The star's gravity creates tidal bulges on the planet. The planet's orbit is not perfectly circular, slightly elliptical. This means tidal forces vary throughout the orbit, sometimes stronger, sometimes weaker. These variations flex the planet. Flexing generates heat through friction. This heat inflates the atmosphere. The planet swells. But tidal heating alone cannot explain the observed inflation. Calculations show tidal heating should contribute some, but not enough to produce such extreme inflation. Something else is happening. Maybe the star's intense radiation penetrates deep into the atmosphere, heats the interior directly. Or maybe the planet has unusual atmospheric composition, chemicals that absorb radiation more efficiently. Or maybe the interior structure is different from standard models. Each explanation has problems. No consensus exists. The planet's surface temperature exceeds 4,000 degrees Fahrenheit on the day side, hot enough to vaporize iron, hot enough to dissociate molecules into atoms. The atmosphere is not just hot, it is being stripped away. Stellar wind and radiation push atmospheric particles into space. The planet is evaporating. Observations confirm mass loss. The planet has a huge extended envelope of material surrounding it. This material is being pulled toward the star, forming a stream. The stream of gas flows from planet to star, feeding the star with planetary material. The star is consuming the planet, literally devouring it. The mass loss rate is estimated at 10 circumflex 23 grams per second, about 189,000 tons every second. That sounds enormous. But the planet's total mass is 10 circumflex 30 grams. At the current loss rate, the planet would completely evaporate in about 10 million years. This is short on cosmic timescales. The star is billions of years old. The planet should have evaporated long ago, yet it exists. This is the WASP-12b paradox. The planet is losing mass too fast to have survived, but it has survived. Something is wrong with our calculations, or something unusual is happening. Maybe the mass loss rate varies? Maybe it was lower in the past, increased recently. But why would it increase? What changed? Another possibility is that the planet is much younger than the star. Maybe it formed recently. Within the last few million years, this would explain why it has not evaporated yet. But forming planets takes time, tens of millions of years typically, and planet formation should be done by the time a star system is billions of years old. WASP-12b's star is mature. Planet formation should have ended long ago. Perhaps the planet formed farther out, then migrated inward recently. Migration takes time too, but catastrophic migration can happen quickly. If another planet existed in the system, a gravitational interaction could have flung WASP-12b inward rapidly. This would explain the recent arrival in a death spiral orbit. But we see no evidence of other planets in the WASP-12 system. This does not mean they do not exist, just that we have not detected them. The planet's orbit is decaying. The tidal forces that heat the planet also transfer angular momentum between planet and star. This causes the orbit to shrink. The planet spirals inward, slowly but measurably. Observations over multiple years show the orbital period decreasing. The planet is falling toward its star, will eventually be consumed, but the timescale is long, several million years. This raises another mystery. If the orbit is decaying now, it must have been decaying for the planet's entire existence. The planet should have started farther out. How much farther? If we run the orbital evolution backward in time, where does the planet start? Calculations suggest it started at a distance of perhaps 3 to 4 million miles, double its current distance, still incredibly close, but slightly less fatal. This implies the planet has always been a hot Jupiter, always close to its star, always experiencing extreme conditions. It did not form in a cool outer region and migrated recently. It formed close and has been close ever since, or migrated early in the system's history and has been in this orbit for billions of years. If the latter, the mass loss calculations must be wrong. The planet must be losing mass slower than estimated, otherwise it would be gone. The planet's atmosphere is bizarre. It contains carbon monoxide, detected spectroscopically. Carbon monoxide forms at high temperatures, expected, but the amount is surprising. Models predict less carbon monoxide. The discrepancy suggests either the temperature is higher than thought, or the carbon-to-oxygen ratio is different. Maybe the planet is carbon-rich. Like 55 Cancri E discussed earlier, a carbon-rich atmosphere changes chemistry. Instead of water vapor, you get carbon monoxide and methane. Instead of silicate clouds, you might get carbide or graphite clouds. The planet's appearance and behavior would differ from oxygen-rich hot Jupiters. This could explain some of the unusual observations, but confirming carbon enrichment requires better spectroscopy, more detailed measurements. The planet's transit provides rich data. When the planet passes in front of the star, starlight passes through the planet's atmosphere. Atmospheric molecules absorb specific wavelengths. This creates absorption features in the spectrum. By analyzing these features, we determine what molecules are present. WASP-12b's transit spectrum shows sodium, potassium, carbon monoxide, and hints of water vapor. Each molecule tells a story about temperature, pressure, and chemistry. But the spectrum also shows something unusual: excess absorption at short wavelengths. Ultraviolet and blue light are absorbed more than expected. This suggests haze. Small particles suspended in the upper atmosphere. The particles scatter short wavelengths efficiently, make the planet appear darker in UV and blue light, brighter in red light. The haze composition is unknown. Could be soot from hydrocarbon reactions, could be metal oxides, could be something exotic we have not considered. The planet's night side is surprisingly hot. Most hot Jupiters have cooler night sides. The day side faces the star, gets blasted with radiation. The night side faces space, should cool radiatively. But WASP-12b's night side temperature is almost as high as its dayside temperature. This implies efficient heat redistribution. Fast winds carry heat from dayside to nightside. Or the planet's interior generates so much heat from tidal friction that surface temperature is dominated by internal energy rather than stellar radiation. If internal heating dominates, the planet is even more unusual than thought. Most planets are heated primarily from outside. Sunlight warms the surface. Some planets have internal heat sources. Earth has radioactive decay. Jupiter has leftover formation heat. but WASP-12b might be heated primarily by tidal friction. The star's gravity flexing the planet generates more heat than the star's radiation delivers. This would be unique among known planets. The magnetic field of WASP-12b is unknown, but it must be interesting. The planet is losing mass. The escaping material is ionized plasma. If the planet has a magnetic field, the field interacts with this plasma, channeling it, constraining it, creating structures, magnetospheric cusps, tail regions. The star's magnetic field also plays a role. The stellar field reaches the planet's orbit, planet and star magnetically connected. Energy flows between them. This could accelerate mass loss or slow it, depending on field configuration. Some models propose that the planet has a cometary tail. Like comets near the Sun, WASP-12b sheds material that streams away in the stellar wind. This tail might be detectable during transit. Extra absorption when the star's light passes through the tail. Observations hint at such absorption, but confirmation requires more data. The tail, if real, would be hydrogen and helium, the lightest elements, most easily stripped by stellar wind. WASP-12b's star is slightly more massive than the Sun. It is also slightly older, evolved. On its way to becoming a subgiant, this evolution affects the planet. As stars age, they grow brighter, more luminous. The increased radiation heats the planet more, accelerates mass loss. The planet's doom is approaching from two directions. Orbital decay spiraling it inward, stellar evolution heating it more intensely. Both processes accelerate. The planet has perhaps a few million years left, maybe less. This makes WASP-12b a transient object, a temporary phenomenon. It will be gone soon, consumed. Its material is absorbed into the star. Future observers will find no trace. Just a slightly unusual stellar spectrum, a bit more hydrogen than expected. A trace of metals, hints that the star once had a planet, but no planet will remain. Yet for now, it exists. This dying world teaches us about planetary destruction, about the end stages of planetary evolution. Most planets die quietly, frozen as their stars cool, or ejected as stars lose mass, or swallowed when stars become red giants. But WASP-12b dies differently, torn apart, evaporated, fed to its star piece by piece. The planet also challenges formation theories. How do planets end up in such extreme orbits? Migration models explain hot Jupiters, but WASP-12b's orbit is too close. Most migration mechanisms predict stopping points farther out. Something must have pushed WASP-12b past the normal stopping point. An additional kick, another planet's gravitational interference, or interaction with the star's magnetic field, or tidal effects stronger than models predict. Each possibility requires specific conditions. Multiple planets for gravitational scattering, strong stellar magnetic fields for magnetic braking, unusual orbital configurations for enhanced tidal evolution. We cannot test these scenarios directly. The planet's early history is lost. We see only the endpoint, the dying phase. Everything before is inference and guesswork. The planet's composition remains uncertain. Is it like Jupiter, mostly hydrogen and helium, or does it contain more heavy elements, higher metallicity? The low density suggests hydrogen and helium dominate, but the inflated size complicates analysis. An iron core could be buried deep inside, surrounded by a rocky mantle, then the hydrogen-helium envelope, or the planet could be entirely gas, coreless, like Jupiter might be. Without knowing composition, we cannot fully model the planet's evolution. Different compositions respond differently to tidal heating. Different atmospheric compositions change heat transport. Different core masses affect orbital decay rates. Everything connects. Each unknown affects calculations. Our understanding is built on assumptions, and assumptions might be wrong. WASP-12b was discovered in 2008 using the transit method, the WASP project. Wide-angle search for planets. Survey telescopes monitoring hundreds of thousands of stars. Looking for periodic dips in brightness. WASP-12b's transits are deep, easy to detect. Follow-up observations confirmed the planet, measured its properties, revealed its extreme nature. Since discovery, WASP-12b has been observed extensively. Ground-based telescopes, Hubble, Spitzer. Every major observatory has studied it because it is extreme, because it challenges theory, because it might not last. Astronomers want to understand it before it disappears. The planet is a natural experiment. Nature pushed conditions to extremes. We watch and learn. Some predictions can be tested. The orbital period should continue decreasing. Measurably. Observations over decades will track the spiral. The mass loss rate might vary. Yearly monitoring could detect changes. The atmospheric composition might evolve as deeper layers are exposed. Time series spectroscopy would reveal compositional evolution. These observations are planned. Data accumulates slowly, but patterns emerge. WASP-12b is not alone. Several other hot Jupiters orbit dangerously close to their stars. WASP-19b, WASP-18b, Kepler 70b. Each is extreme, each losing mass, each on a death spiral. But WASP-12b is the most studied, the benchmark for understanding planetary destruction. Its fate is their fate. Its mysteries are their mysteries. These doomed planets raise philosophical questions. Why do they exist at all? If they are doomed, why did nature make them? The answer is probability. In a universe with trillions of planets, rare events happen. Planetary orbits sometimes evolve to extremes. Most planets are stable, a few are not. We observe the unstable ones because they are interesting, because they teach us about limits. The existence of doomed planets also tells us something about timescales. Planetary systems evolve. They are not static. Planets migrate. Orbits change. Some planets are destroyed. Others survive. The configurations we observe now are snapshots, temporary arrangements. In a billion years, the solar system's configuration will differ from today, not drastically, but measurably. Over cosmic time, everything changes. WASP-12b's death is slow, millions of years, but it is happening. We are witnessing planetary destruction in real time. Not the sudden impact that killed the dinosaurs. Not the gradual cooling of a planet as its star dies, but active consumption. The star is eating its planet, day by day, orbit by orbit, until nothing remains. This is the fate of all planets that wander too close. Gravity is unforgiving. Tidal forces are relentless. WASP-12b crossed a line, entered a regime where destruction is inevitable. Now it cannot escape, cannot reverse course. It can only fall, evaporate, dissolve into the star that birthed it billions of years ago. Yet the planet persists. Against odds, against predictions, it should not exist. But it does. For now, for a few million years more. Long enough for us to study it. Long enough to learn what happens when planets die. Long enough to see the end coming but not arrive. WASP-12b is a planet on death row, condemned but not yet executed, walking toward oblivion one orbit at a time. This is what makes it mysterious, not what it is, but that is it, existing in conditions that should have destroyed it, defying extinction through mechanisms we do not fully understand. The planet that should not exist. But anyway, teaching us that the universe is stranger than our theories, that nature finds solutions we do not anticipate, that even doomed worlds can persist long enough to become mysteries. The frozen giant that broke physics. Uranus broke physics, not figuratively, literally. When Voyager 2 flew past in 1986, It measured properties that contradict established theory. The planet's magnetic field is impossible. Its heat flow violates thermodynamics. Its rotation defies angular momentum conservation. Every measurement raises questions that remain unanswered decades later. Uranus is not just mysterious, it is wrong. Start with the magnetic field. Planetary magnetic fields are generated by conducting fluids in the interior. Earth's field comes from molten iron in its outer core. Jupiter's field comes from metallic hydrogen. These fields have specific properties. They align roughly with the planet's rotation axis, tilted maybe 10 to 15 degrees at most. They are dipolar, north and south poles, like bar magnets. Uranus's magnetic field is tilted 59 degrees from its rotation axis. Not 10 degrees, 59 degrees. This is not a small deviation. This is fundamental misalignment. The north magnetic pole is closer to the equator than to the geographic North Pole. The field is also offset. It does not originate at the planet's center. It is offset by about a third of the planet's radius. The field is not dipolar. It has significant quadrupole and octupole components, multiple poles, complex structure. No dynamo theory predicts this. Dynamo models work for Earth, Jupiter, Saturn, even Neptune to some extent, but not Uranus. The only way to generate such a field is if the conducting region is not in the deep interior. It must be in the outer layers. In the mantle, but Uranus's mantle is supposed to be water, methane, and ammonia ice, non-conducting, or at most, weakly conducting. Some models propose superionic ice, a strange phase of water where oxygen atoms are locked in a lattice, but hydrogen ions move freely. This phase conducts electricity, could generate magnetic fields, and it exists at the pressures and temperatures expected in Uranus's mantle, so maybe the conducting layer is superionic ice, and maybe its convection patterns are unusual, creating the tilted offset field. But superionic ice is speculative. We have not confirmed it in laboratories at the required conditions. The phase exists theoretically. Computer simulations predict it, but direct evidence is lacking. And even if superionic ice exists, why does it create such an unusual field? Convection should be organized by rotation, should align with the rotation axis. Uranus's field does not. Another proposal involves the planet's formation. Maybe Uranus was hit by a large object early in its history, a collision massive enough to knock the planet on its side. Uranus's rotation axis is tilted 98 degrees. It rotates on its side, spinning like a barrel rolling down a hill. This extreme tilt is unique in the solar system. A giant impact could explain it. If the same impact disrupted the interior structure, it might explain the magnetic field. The impact could have stirred up layers, mixed materials that should be separated, created irregular density distributions. These irregularities would affect convection, lead to unusual magnetic field generation. The impact happened billions of years ago, but its effects persist. However, giant impact theory has problems. Simulations show that impacts large enough to tilt Uranus should also heat the planet significantly, deliver enormous energy. That energy becomes heat. The planet should be hot, should radiate excess heat for billions of years, like Jupiter and Saturn do. But Uranus does not. Uranus radiates almost no excess heat. Energy output matches solar input almost perfectly. The planet is in thermal equilibrium. No internal heat source. This is the second impossible feature. Planets Uranus's size should still be cooling from formation, should radiate excess heat. Neptune does. Neptune and Uranus are similar in size and composition, both formed at the same time. Both should have similar cooling rates, but Neptune radiates excess heat, Uranus does not. This discrepancy has no good explanation. Either Uranus formed colder than Neptune, or it cools much slower, or something removed its internal heat. Each possibility has problems. Uranus and Neptune formed from similar materials at similar distances from the Sun. They should have similar formation temperatures, and the cooling rate depends on size and composition. Uranus and Neptune are nearly identical in both. Cooling rates should be similar. The third option is most mysterious. What could remove internal heat? Where would it go? Heat cannot just disappear. It must be conducted, convected, or radiated away. If Uranus cooled faster in the past, heat flow would be enhanced. But what enhances heat flow then stops it? No known mechanism works. Some scientists propose layering. Maybe Uranus's interior is stratified, separated into distinct layers that do not mix. These layers suppress convection. Without convection, heat transport is inefficient. Heat stays trapped in the interior, cannot escape efficiently. This would make the planet appear cold from outside, even if the interior is still warm. But why would Uranus be stratified while Neptune is not? They formed similarly, have similar compositions, should have similar interior structures, unless something happened to one but not the other. An impact, a close encounter with another planet, something that disturbed Uranus but not Neptune. This brings us back to giant impact theory, but with the caveat that the impact must have created stratification without delivering too much heat. A very specific type of impact, possible but unlikely. Uranus's rotation axis is the third impossibility. A tilt of 98 degrees means the planet orbits the Sun on its side. During summer, one pole points nearly directly at the Sun, stays in sunlight for 42 Earth years. The other pole faces deep space, darkness for 42 years. Then the situation reverses. This creates extreme seasonal variations. Summer and winter at the poles are more extreme than anywhere else in the solar system. Such a tilt requires explanation. Planets form with rotation axes roughly perpendicular to their orbital planes. Conservation of angular momentum from the protoplanetary disk. Small tilts can develop from gravitational interactions with other planets, or from moons, but 98 degrees is not a small tilt. This requires catastrophic events. Giant impact is the favoured explanation. A Mars-sized object hit Uranus during formation. The collision transferred angular momentum, knocked the planet over. Computer simulations show this is possible. The right size impactor at the right angle and velocity can produce the observed tilt. But the same simulations predict other consequences. The impact should create a debris disk. That debris should form moons. Uranus has moons, 27 of them. The 5 largest are substantial. Could they have formed from impact debris? The moon orbits are aligned with Uranus's tilted equator. If they formed from an impact debris disk, that disk must have been aligned with Uranus's post-impact rotation. This works. But the moon's compositions should reflect the impactor's composition. We do not know the moon's compositions precisely, but they seem to be ice and rock, similar to Uranus itself, similar to other outer solar system objects, not obviously unusual. This neither confirms nor refutes giant impact. The extreme tilt affects atmospheric circulation. On Earth, solar heating is strongest at the equator. This drives atmospheric circulation, Hadley cells, Ferrel cells, organized patterns. On Uranus, solar heating is strongest at whichever pole faces the Sun. During summer, one pole gets constant sunlight for decades. The equator gets sunlight at grazing angles. This should create completely different circulation patterns. Yet Voyager 2 found that Uranus's atmosphere has a banded structure similar to Jupiter and Saturn. Dark and bright bands parallel to the equator. Wind velocities organized by latitude. Maximum winds at mid-latitudes. These patterns suggest the atmosphere is more influenced by internal heat and rotation than by solar heating. But Uranus has no internal heat, So what drives the circulation? The atmosphere is mostly hydrogen and helium, with about 2% methane. Methane absorbs red light, reflects blue and green. This gives Uranus its cyan color. But the methane distribution is unusual. More methane at the equator, less at the poles. This suggests vertical mixing varies with latitude. Equatorial regions have more vigorous convection, dredging up methane from deeper layers. Polar regions have weaker convection. Less methane reaches observable altitudes. But why would convection vary by latitude on a planet with no significant internal heat? Solar heating is weak at Uranus. The planet is 19 astronomical units from the Sun. Solar flux is 1/400th of what Earth receives. Yet the atmosphere is dynamic. Winds reach 560 miles per hour, faster than Earth's worst hurricanes. Storms form and dissipate. Cloud features come and go. All this activity requires energy. Where does it come from? Some scientists propose that the atmosphere has its own internal heat source, not from the deep interior, from chemical reactions in the atmosphere itself. Methane photochemistry. Solar ultraviolet breaks methane molecules. Carbon and hydrogen recombine in various ways. Some reactions release energy. This energy might drive circulation, but calculations show photochemical energy is small, not enough to power the observed wind speeds. Another possibility involves seasonal effects. Even though Uranus receives little solar energy, the extreme seasons create temperature gradients. One pole bakes in sunlight for 42 years. Heats up. The other pole freezes in darkness. Cool down. This creates pressure differences. Air flows from high to low pressure. Winds result. Over decades, these winds build, become organized, create the observed circulation patterns. Recent observations support this. Ground-based telescopes monitoring Uranus over years have detected increasing atmospheric activity. More storms, brighter clouds. This increased activity coincides with Uranus's 2007 equinox, when the Sun crossed the planet's equator. Transitioning from southern summer to northern summer, the changing solar illumination might be driving atmospheric changes, with a decades-long lag due to the planet's thermal inertia. Uranus's interior structure is poorly constrained. Models assume a rocky core, surrounded by an ice mantle, then a gas envelope. But the masses and boundaries of these layers are uncertain. Voyager 2 did not carry instruments to probe the interior directly. Gravity measurements give total mass and density, but cannot distinguish between different internal structures that have the same total mass. Improved models suggest the ice mantle is not pure water ice. It is a mixture of water, methane, and ammonia. At the pressures and temperatures inside Uranus, these materials do not form normal ice. They exist as superionic ices or fluid mixtures, dense fluids rather than solid ice. This affects heat transport, affects electrical conductivity, affects everything. The boundary between the ice mantle and gas envelope might not be sharp. Instead of a distinct surface, there might be a gradual transition. Composition and density change smoothly over a range of depths. This would affect how the planet responds to tidal forces, how it vibrates, how sound waves propagate through it. Seismic measurements could constrain structure. But we cannot put seismometers on Uranus. We can only observe from afar. Uranus's rings are faint and narrow. Discovered in 1977 when the planet occulted a star. Astronomers watching the star saw it flicker before and after Uranus passed in front. The flickers were light blocked by rings. Voyager 2 imaged the rings directly, found 13 distinct rings. Most are just a few kilometers wide, made of dark particles, reflecting very little light. The rings are narrow because shepherd moons confine them. Small moons orbit just inside and outside some rings. Their gravity keeps ring particles from spreading. This is similar to Saturn's rings. But Uranus's rings are different. Darker, narrower, more circular. We do not fully understand why. The dark color suggests organic compounds. Radiation processing of methane produces complex hydrocarbons. These coat the ring particles, turn them dark. The ring's origin is unclear. Did they form with Uranus? Or later from disrupted moons? Or captured objects? Ring particles cannot last forever. Collisions grind them down. Plasma drag causes them to spiral inward. The rings must be replenished, or they are young, formed relatively recently, within the last few 100 million years. This would explain why they still exist, but raises questions about what created them. Uranus has been visited by one spacecraft, Voyager 2 inches, January 1986. The flyby lasted a few hours. The distance of closest approach was 50,600 miles. Voyager 2 measured magnetic fields, took images, observed occultations, measured atmospheric composition. All our close-up data comes from that one flyby, decades ago. A return mission to Uranus is considered a priority by planetary scientists. NASA and ESA both have studied concepts: an orbiter mission, atmospheric probe, maybe even landers on moons. Such a mission would revolutionize understanding, measure gravity field precisely, map the interior, monitor magnetic field variations, study atmospheric dynamics over multiple seasons, observe the moons in detail. But Uranus is far away, 19 astronomical units, travel time is 10 to 15 years, mission cost is high, billions of dollars. Competing priorities exist: Mars, Europa, Titan. Asteroids, resources are limited. Uranus waits, patient, cold, mysterious. The planet that broke physics remains broken. Its magnetic field defies explanation. Its thermal state contradicts theory. Its rotation axis is impossible. Its atmospheric dynamics make no sense. Each mystery connects to others. Solving one requires understanding all, and we do not. Not yet. Maybe not for decades. Uranus is a reminder that the solar system still holds secrets, that we do not understand everything. Those planets we have known about for centuries can still surprise us, challenge us, show us that nature is more complex than our models, more strange than our theories, more mysterious than we want to admit. The frozen giant spins on its side, silent, inscrutable, waiting for us to understand, or waiting for us to admit we cannot. Uranus does not care which. It will keep spinning, keep orbiting, keep defying explanation, until we finally figure it out, or until the sun dies and takes all its planets with it. Whichever comes first. Moons in detail. But Uranus is far away, 19 astronomical units. Travel time is 10 to 15 years. Mission cost is high, billions of dollars. Competing priorities exist: Mars, Europa, Titan. Asteroids, resources are limited. Uranus waits, patient, cold, mysterious. The planet that broke physics remains broken. Its magnetic field defies explanation. Its thermal state contradicts theory. Its rotation axis is impossible. Its atmospheric dynamics make no sense. Each mystery connects to others. Solving one requires understanding all, and we do not. Not yet. Maybe not for decades. Uranus is a reminder that the solar system still holds secrets, that we do not understand everything. Those planets we have known about for centuries can still surprise us, challenge us, show us that nature is more complex than our models, more strange than our theories, more mysterious than we want to admit. The frozen giant spins on its side, silent, inscrutable, waiting for us to understand, or waiting for us to admit we cannot. Uranus does not care which. It will keep spinning, keep orbiting, keep defying explanation, until we finally figure it out, or until the sun dies and takes all its planets with it, whichever comes first. The rogue worlds that wander alone. Not all planets orbit stars. Some drift through interstellar space, alone, unbound to any sun, wandering the galaxy in darkness. These are rogue planets, orphaned worlds, ejected from their birth systems. Condemned to eternal night. We have found them. Not many. They are difficult to detect. No star to transit. No radial velocity signal to measure. We rely on gravitational microlensing or direct imaging. Both methods are inefficient. It requires luck. But they work, and they reveal a surprising truth. Rogue planets are common, perhaps more common than stars themselves. The first confirmed rogue planet was discovered in 2000, CFBD-SIR 2149, about 4 to 7 Jupiter masses, floating in space, no star nearby. Temperature around -100 degrees Fahrenheit, cold but not frozen solid. The planet still retains heat from formation, glowing faintly in the infrared. Detection by sensitive telescopes. Since then, dozens have been found. Some are gas giants, Jupiter-like, others smaller, perhaps terrestrial, rocky worlds wandering alone. Each discovery raises the same question. Where did they come from? The standard answer is ejection. Planets form in systems around stars, but gravitational interactions can eject them. Three-body dynamics. If two planets pass close, one gains energy, moves to higher orbit, the other loses energy, gets ejected, or falls into the star. This is common in simulations. Young planetary systems are chaotic. Planets migrate, orbits cross. Encounters happen. Some planets are expelled. Computer models suggest 1 to 2 planets per star system are ejected during formation. This predicts trillions of rogue planets in the galaxy. More rogue planets than planets orbiting stars. Most of the galaxy's planets are in interstellar space, not bound to stars. This is remarkable. The universe's planetary population is dominated by wanderers, not by worlds with suns. But ejection is not the only mechanism. Some rogue planets might form in isolation, not in protoplanetary disks around stars, but in molecular clouds, dense regions of interstellar gas. If a cloud region becomes gravitationally unstable, it can collapse directly into a planet-sized object. No star required. This is called turbulent fragmentation. It creates free-floating objects from the start. These objects blur the line between planets and brown dwarfs. Brown dwarfs are failed stars, not massive enough to ignite hydrogen fusion, but formed like stars through gravitational collapse. Planets form in disks through accretion. The formation mechanism defines the category. But isolated objects could form either way. We cannot tell which just by looking. Some scientists propose a mass boundary. Objects below 13 Jupiter masses are planets. Above that are brown dwarfs. This boundary is where deuterium fusion becomes possible, but it is arbitrary. Formation history matters more than mass. A 10 Jupiter mass object formed through turbulent fragmentation is more brown dwarf than planet. Even if its mass is below the threshold, the terminology debate is not just semantic, it affects how we count planets. If turbulent fragmentation produces planet mass objects, then rogue planets are more common than ejection alone predicts, perhaps 10 to 100 times more common. The galaxy could contain 100 billion to 1 trillion rogue planets, far outnumbering bound planets. These wanderers are cold, no star to warm them, their surfaces are frozen, but some might have subsurface oceans. Heat from radioactive decay in the core could keep water liquid beneath thick ice shells, like Europa, like Enceladus, but without the tidal heating, just radioactivity, providing enough heat to prevent complete freezing. A rogue Earth-mass planet with Earth-like radioactivity could maintain a subsurface ocean for billions of years. The surface would be frozen, ice hundreds of kilometers thick, but below, liquid water. And where liquid water exists, life might be possible, not photosynthetic life, no sunlight, but chemosynthetic life, using chemical energy, like hydrothermal vent ecosystems on Earth. This is speculative. We have no evidence of life on rogue planets, but the possibility exists, and it is fascinating. Life without a sun, surviving on geothermal heat alone, in eternal darkness. Never seeing stars, never experiencing day or night, just perpetual twilight in a subsurface ocean under kilometers of ice. Some rogue planets might have moons. If a planet is ejected, its moons could come along, bound by gravity, continuing to orbit the planet even after ejection. These moons would be worlds unto themselves. Orbiting a planet that orbits nothing, the moon's sky would be dominated by the planet. No sun, just the faint glow of the rogue world and the stars beyond. Tidal heating might be stronger in rogue planet-moon systems. Without a star, the planet-moon system is isolated. Tidal forces between the planet and moon could exchange energy, heating both bodies. This might create more favorable conditions for subsurface oceans, or even surface liquid if the heating is strong enough. Though without sunlight, surfaces would still be dark. The discovery rate of rogue planets is limited by technology. Gravitational microlensing surveys detect them randomly. A rogue planet passes in front of a background star, its gravity bends light, magnifies the star briefly. We see the magnification event, calculate the planet's mass, but we get no location. The planet is somewhere along the line of sight. We cannot follow up, cannot study it further. One and done. Direct imaging works better for young planets. Newly formed planets are hot. They glow in the infrared. Telescopes can detect them if they are close enough and the background is dark enough. This method has found several young rogue planets within a few hundred light years, but older planets are cool. Their thermal emission fades. They become invisible, only detectable through rare microlensing events. The Nancy Grace Roman Space Telescope will search for rogue planets. Launching in the late 2020 seconds, it will conduct a microlensing survey, monitor millions of stars, detect thousands of rogue planets, estimate their masses and distances statistically. This will constrain the rogue planet population, tell us how common they are, what mass distribution they have. Some rogue planets might be captured by stars. A rogue planet drifting through space passes near a star. Gravitational interaction. If the planet loses enough energy, it becomes bound. Enters orbit. Becomes a regular planet. This is rare. Requires precise conditions. But it is possible, and it might explain some orbital oddities. Triton, Neptune's largest moon, orbits backward. Retrograde. This suggests Triton was captured. Originally a Kuiper Belt object, or possibly a rogue planet. Neptune's gravity caught it. Tidal forces circularized the orbit over time. Now Triton is Neptune's moon, but it started elsewhere, a wanderer that found a home. If Triton can be captured, so can other rogue planets. The solar system might have captured objects, planets or large moons that originated elsewhere, wandered through interstellar space, entered our system, got caught. We cannot identify them easily, but they might be here. Some scientists speculate about Planet 9, a hypothetical planet beyond Neptune, invoked to explain unusual Kuiper Belt object orbits. Planet 9, if it exists, might be massive. 5 to 10 Earth masses, in a distant orbit. Perhaps it is a captured rogue planet, born in another system, ejected, wandered for millions of years, then captured by the Sun. This would explain its unusual orbit, highly eccentric, highly inclined, not like the other planets. Planet 9 remains unconfirmed. Searches continue, but finding a dark planet in the outer solar system is difficult. It reflects almost no light, moves slowly, could be anywhere in a huge volume of space. Telescopes scan systematically, but it will take years to cover the search area. Rogue planets complicate the definition of planet. The International Astronomical Union defines planets as objects orbiting stars. This excludes rogue planets. They are not planets according to the official definition, but calling them rogue planets implies they are planets. The terminology is inconsistent. Some scientists propose sub-brown dwarf as a better term. These objects are below the brown dwarf mass threshold, but formed like brown dwarfs through collapse, not accretion. This separates them from planets by formation mechanism, but most people still call them rogue planets. The name is catchier, more evocative, easier to communicate. The existence of rogue planets forces us to broaden our conception of worlds. Not all planets have skies lit by suns. Some have only starlight, faint, distant. The surface is frozen. The interior might be warm, but the environment is hostile. No light, no warmth, just cold and darkness. Yet these worlds exist. They are real. They outnumber the planets we usually think about. The galaxy is full of them, wandering, unseen, unknown. Each is a world with its own history. Formed somewhere, ejected or never bound, travelling through the galaxy for billions of years, maybe forever. Some rogue planets will eventually leave the galaxy. Gravitational interactions can accelerate objects to galactic escape velocity. These planets will enter intergalactic space, true wanderers. Between galaxies, even farther from any star, even more isolated, drifting through voids that stretch for millions of light years. In the far future, the universe will be dominated by rogue planets. Stars will burn out. Galaxies will separate. Accelerating expansion will isolate galaxies from each other. But planets will persist, frozen, dark, alone, drifting through an expanding void. The universe's final state might be a cold collection of rogue planets, scattered through infinite space, each carrying the faint memory of when the cosmos was young and bright. This is billions or trillions of years in the future, but rogue planets today are a preview. They show us the end state, cold worlds without stars, surviving on residual heat or radioactive decay, or nothing at all, just frozen hulks in the dark. And yet they fascinate, because they exist, because they remind us that planets are not defined by their stars. That world can be independent, that not all of creation is bound to light. Some of it wanders, free, alone, mysterious. The rogue worlds that orbit nothing, that belongs nowhere. That drifts forever through the dark between the stars. The planet where it never stops raining. Gliese 1214b orbits a red dwarf star 48 light-years from Earth. The planet is 3 times Earth's radius, 7 times its mass. It completes one orbit every 38 hours. Surface temperature around 450 degrees Fahrenheit. Hot, but not scorching. Not hot enough to vaporize water. And the planet contains enormous amounts of water. The planet is sometimes called a water world, covered entirely by ocean. No continents, no land, just water from pole to pole. Except the water is nothing like Earth's oceans. The pressure is too high, the temperature is too extreme, the water exists in exotic phases, supercritical water, plasma, Ice 7, forms that have no equivalent on Earth. The planet's density reveals its composition. About 2 grams per cubic centimetre, too low for pure rock, too high for pure hydrogen and helium. The only explanation is substantial water content. Models suggest the planet is about 75% water by mass. The remaining 25% is rock and metal. A small rocky core surrounded by an immense water envelope, then a thick hydrogen-helium atmosphere on top. But this raises questions. Where did all the water come from? Planets in the inner regions of star systems, close to their stars, form from dry materials. Water ice sublimates. Only rock and metal remain. Water-rich planets form beyond the frost line, where temperatures are low enough for ice to condense. Gliese 1214b orbits close to its star. Inside where ice should exist, how did it accumulate so much water? The answer is migration. The planet formed farther out, beyond the frost line. Where ice was plentiful, it grew massive, captured huge amounts of water ice, then migrated inward, brought its water with it. Now it orbits close to the star, in a region where water worlds should not exist. But it does anyway, because it came from elsewhere. This makes Gliese 1214b a super-Earth and a sub-Neptune simultaneously. Its size is between Earth and Neptune. Its composition is unique, not rocky like Earth, not gaseous like Neptune. Something in between, a water world. A new category of planet that we never knew existed before discovering exoplanets. The atmosphere is thick, hundreds of miles deep, but observations show it is featureless. No spectral features, no absorption lines from expected molecules like water vapor, methane, or carbon dioxide. Just a flat, featureless spectrum. This was surprising. Every planet with an atmosphere should show spectral features. Gliese 1214b does not. The explanation is clouds, or haze. High-altitude particles that obscure the lower atmosphere. Light cannot penetrate. It scatters off the haze particles instead. No photons reach the deeper layers where molecules absorb. So we see no molecular signatures, just the haze, opaque and uniform. But what creates the haze? On Earth, haze forms from organic molecules, smog, pollution, natural hydrocarbons in the atmosphere reacting with sunlight. On Titan, haze forms from methane photochemistry. But Gliese 1214b is much hotter than Titan, and probably lacks significant methane. The haze must be something else. One proposal is water clouds. At certain altitudes, temperature and pressure allow water vapor to condense, form clouds. These clouds could be thick enough to obscure everything below, but water clouds are not uniform. They have structure, variations. Gliese 1214b's spectrum is too flat, too featureless. Water clouds alone cannot explain it. Another idea involves heavier molecules, potassium chloride, zinc sulfide. These condense at the temperatures in Gliese 1214b's upper atmosphere, form hazes similar to those on Earth, but made of vaporized rocks instead of organics. Rock hazes, vaporized minerals suspended in the air, creating a thick, opaque layer that blocks light. This rock haze hypothesis fits observations, but it requires significant amounts of vaporized rock in the atmosphere. Where does it come from? From the planet's surface? But the surface is ocean. Water does not contain significant rock. Unless the ocean is not pure water, maybe it is a brine, saturated with dissolved minerals. These minerals evaporate, enter the atmosphere, form haze. Or maybe the atmosphere is not what we think. Some models propose that Gliese 1214b's atmosphere is mostly hydrogen and helium, like a mini Neptune. With only trace amounts of water vapor, this would also produce a flat spectrum if heavy molecules formed high-altitude hazes. But it contradicts the density measurements. The planet's overall density requires substantial water, unless the water is all in the interior, not in the atmosphere, locked in a deep ocean beneath a hydrogen atmosphere. This layered structure is possible, a rocky core, surrounded by a high-pressure water ocean, then a dense steam atmosphere, then hydrogen and helium on top, each layer separated by pressure and temperature gradients, but mixing between layers should occur. Convection should transport material, unless something suppresses mixing, creates stable stratification. The planet's ocean, if it exists, is bizarre. At the surface, water might be liquid, but pressure increases with depth. Below a certain depth, water transitions to ice. Not normal ice. Ice 7. A high-pressure ice phase where water molecules arrange in a specific crystal structure. Ice 7 is solid, but hot, several hundred degrees. Hot ice. It sounds contradictory, but is real. Pressure forces water into a solid state, despite high temperature. Below the ice, the 7 layer might be more exotic phases. Ice 10. Ice 10. Even more compressed water. Eventually, at extreme pressures, water molecules dissociate, break apart into hydrogen and oxygen. These elements might separate, form layers, or react, form new compounds, hydrogen peroxide, hydroxide. Chemistry at these pressures is uncertain. Experimental data does not exist. We rely on computer simulations, quantum mechanical calculations, best guesses. The planet's interior structure affects its evolution. If water layers are stable, the planet cools slowly and the convection would stabilize. Heat flow would slow. The planet would cool gradually over billions of years. But if layers mix through some process we don't understand, the interior could remain dynamic, active, capable of sustaining geological processes that reshape the surface. The ocean itself might be stratified, different layers at different pressures and temperatures, some liquid, some solid, in exotic high-pressure ice forms. Between these layers, chemical reactions could occur, organic molecules forming and breaking down. Energy flowing through the system in ways that mirror primitive metabolism. This is speculation built on fragments of data. Gliese 1214b sits 48 light-years away. We cannot visit, cannot sample, cannot drill through that thick atmosphere to touch the ocean below. What we know comes from light. The planet passes in front of its star. Starlight filters through the atmosphere. We analyze that light, extract information about molecules, particles, clouds, but the atmosphere is opaque. The clouds or haze block deeper layers. We see only the top. Everything below remains hidden. Scientists propose missions with more powerful telescopes, instruments sensitive enough to detect faint spectral features, chemical fingerprints that reveal what lies beneath the haze. James Webb Space Telescope has begun observing Gliese 1214b. Its infrared vision penetrates atmospheric layers better than visible light. Early data suggests the haze might be made of complex hydrocarbon molecules, photochemistry driven by stellar radiation. But confirmation requires more observations, more analysis, more time. The planet represents a class of worlds we never predicted. Water worlds that challenge our definitions of what planets can be, not rocky like Earth, not gaseous like Neptune, something entirely different. A reminder that the universe's creativity exceeds our imagination, that nature builds worlds in ways we're only beginning to understand. Gliese 1214b orbits its star endlessly, locked in eternal dance, rain falling through that thick atmosphere, through clouds we cannot see, into oceans we cannot touch. The drops merge with the water below, become part of something larger. The ocean that covers the world, that is the world. That defines the world. And somewhere in those depths, under pressures that would crush any submarine we could build, in absolute and eternal, the planet keeps its secrets, the chemistry of its formation, the structure of its interior, the possibility, however remote, that something living might exist there. For now, Gliese 1214b stands as a monument to mystery, a world where it might rain forever, where oceans might stretch forever, where questions remain forever just beyond our instruments' reach. A planet that shows us how much we have yet to learn, how far we have yet to go, how many wonders still wait in the darkness between stars. The universe does not build planets according to our expectations. It creates worlds that defy our models, challenge our theories, shatter our assumptions about what is possible. Neptune radiates heat it should not have. Venus spins backward for reasons unclear. Jupiter might have no core at all. Cancri could be wrapped in diamond. HD 189733b rains glass sideways at thousands of miles per hour. WASP 12b should have been destroyed long ago, yet persists. Uranus broke every rule we thought we understood. Rogue planets drift alone through eternal darkness. Gliese 1214b might be an endless ocean wrapped in impenetrable haze. Each of these worlds exists, confirmed by observation, measured by instruments, real beyond doubt. And each one teaches the same lesson, that our understanding of planets was too narrow, too limited, too shaped by the handful of worlds we've known since childhood. The solar system contains 8 planets, but the universe contains trillions. Each one is an experiment in physics, a test of what matter can do under extreme conditions. Some will resemble Earth. Others will be unlike anything we've imagined. The strange planets we've discovered so far are probably the beginning. The universe has barely started showing us what it can create. These mysterious worlds remind us why we explore, not just to catalogue objects, not just to measure properties, but to confront the unknown, to find the places where our knowledge breaks down, where our theories fail, where reality exceeds imagination. Every impossibility we discover expands what we know is possible. Every mystery solved reveals deeper mysteries waiting. The planets that confuse us today might be understood tomorrow. But that understanding will come with questions we cannot yet ask, problems we cannot yet imagine, wonders we cannot yet conceive. The most mysterious planets in the universe are out there now, orbiting distant stars, hidden in clouds, locked in darkness, waiting for better telescopes, better instruments, better theories, waiting for us to find them, to study them, to learn from them. And when we do, they will show us once again that the cosmos is stranger, more diverse, more beautiful than we ever thought possible. The universe builds worlds we call impossible, then proves they exist, and invites us to explain how. That invitation remains open. The mysteries remain unsolved. The planets remain strange. And somewhere in the darkness, worlds beyond imagining wait to be discovered. Wait to challenge everything we think we know. Wait to show us that impossible is just another word for not yet understood. The search continues. The questions multiply. The universe keeps its secrets well, but occasionally it lets one slip, reveals one impossibility, shows one mystery, and reminds us why we look up at the stars with wonder. Because out there, in the vast darkness between suns, planets are doing things they should not do, existing in ways they should not exist, defying laws they should obey, and every single one of them is real.